Good evening and welcome to our first lecture on TE262 Electromagnetic Field Theory. And today's lecture is an introduction to the course. We will get to understand what is electromagnetic field theory and what is entailed in this course. So my name is Abdulrahman Ahmed, and my email address, my telephone number, you can reach me on this. And all course materials are available on this link. And the teaching assistant, who is Clifford, that's his phone number, and then his email, you can also reach him on those contacts. So what is electromagnetic field theory? Electromagnetic field theory, EM field theory for short, it is a study of electric, note that electric and magnetic phenomena caused by electric charges at rest or in motion. So as we have electro and magnetic, then we know the phenomenon that creates these fields that we're talking about are electric phenomenon and magnetic phenomenon. And it is called electromagnetic because the electric and the magnetic field coexist. They are generated and they coexist together. So you have the electric field coupled with the magnetic field. And that is why we have electromagnetic field. And the study of this field is called electromagnetic field theory. Now you can see that from this definition, we say the field is caused by what? Electric charges at rest or in motion. So whether it is the electric field or the magnetic field, the true origin of the field is electric charges. And we'll come to understand that better as we go along in this course. One will think that we should talk about maybe magnetic stones as being responsible for the magnetic phenomena. But as we go along, we'll come to understand that the actual origin of all the fields, both electric and magnetic, is electric charges. Now, if I should say something about this to make it a bit clearer, you are aware that you can actually create a magnetic material from electricity. So in a case where you have a magnetic material, for example, like this, and then you pass some solenoid on it. There are some wires around it. So these wires, if they are energized, the coils, if they are energized by some electric source, and then this bar of magnet is moved to and fro, it will become magnetized. And the source of the magnetization then is what? Electric, since it was created by electric field. So even though we have both magnetic and electric phenomenon, they are all caused basically by what? The electric charges, either when they are at rest or in motion. If we look at electric charges at rest, that study is called what? Static electric field. Static. That is when the charges are at rest. And when they are in motion, then we are looking at dynamic fields. Our study will first look at static electric fields, and then later we'll look at time-changing fields. And the time-changing fields will be taking care of the dynamic nature of the field. So in this sense, the theory or the study of electric and magnetic phenomena, which is caused by electric charges at rest or in motion, is called electromagnetic field theory. So what is the history of electric charges, which are the origin of the electric and the magnetic field. Now, we know from history that it was this man, Thales of Miletus, who discovered that when you rub amber rod on a silk or wool, you'll see that the amber begins to attract straw and small bits of paper. And here in Ghana, we understand this phenomenon usually during Hamatan. So when you wear a cloth, and by moving in this cloth, you're rubbing your skin against the cloth, and the cloth is rubbing itself also part by part. And then you realize that it begins to attract things because charges have been developed on that material. And therefore, this man, Thales of Miletus, he discovered that the amber rod, after being rubbed with wool or silk, is able to attract straw of material. Now, the Greek word for amber is electron, I think spelled with K. It's electron, from which was derived electron, electronics, and electricity. And all of these fields emanate from that. So the electric charge, which is the origin of all fields, as we have discussed, was first discovered by this man, Thales of Miletus. Now, so what aspect of it is the field? I think the most common understanding we have of a field, for example, is a football field. A football field, usually drawn or usually in a rectangular form, like that. It's called a field because that is the extent within which the ball must be played. The ball must not be played to go outside of this field. So when we talk about fields relating to electric and magnetic phenomenon, then we are talking about the region of space within which the effect of the field can be felt. So if you had a bar of magnet, for example, like this, there is a region around this bar of magnets within which the force of the magnet can be felt. This region is called the field of the magnet. So the field is actually an area within which the force of the electric phenomenon or the magnetic phenomenon can be felt. Practically speaking, a field is the kind that is created by a BTS or base transceiver station. Your mobile phone is able to connect to a network because you are within the field of this BTS, if I represent that by a big antenna like this. So this antenna will create a field around it. If you are within that field, you will receive signal from the base transceiver station. If you go out of that field, let's say you're driving and you go out of that field, then you go out of the coverage area of the BTS. You go out of the field of the BTS, and then you can no longer receive signals. So the region around the BTS where signals can be received or where the field can be felt is what we call in the field. And therefore, electric and magnetic phenomenon within a given region of space, the study of that is called electromagnetic field theory. I hope this helps us understand what the course basically mean. And if we should take this a bit further, the fact that we are talking about a field, like the signal from a telephone cell tower, for example, then we are talking about a situation where the field is spaced out in space, and there's variation in space as well as variation in time. So as we move away from the tower, the strength of the field keeps reducing, right? That's a variation. until the edge of the tower or at the edge of the cell where you can still receive the field. Beyond that, you cannot receive the field because the field has been changing and reducing as you move away from the center. The same way also in time, the field is also changing. So it changes both in time and in space. So if you draw, for example, a sine wave like this, if this is 0, at a certain point, if this is given by as the field, you see at a certain point, the amplitude of the field is 0. But as time changes, the amplitude is increasing, then decreasing, and then increasing again. So the field may be changing both in space and time. And that is what adds a little bit of complication to this course, because we are analyzing quantities that are changing in space and in time. But there are some concepts which I believe that if we focus on understanding those concepts, I believe that this course will come a bit handy. So we continue. We look at the source of the electromagnetic field, which is what? The electric charge. This electric charge can either be positive or negative. So if you take an atom, for example, an atom has electrons and protons. The electrons will give us negative charges and the protons will give us positive charges. So the electric charge is either a positive charge or a negative charge. And this charge is the source of the electric field. And we are also aware from circuit theory that when you have moving charges, they produce a current. So that if this current is time varying, as I indicated before, then it will give rise to a magnetic field as well. You remember I draw a bar which had a solenoid or a coil around it, and if the field is changing, it will create a magnetic field in the bar. So if the current is time varying, it will give rise to a magnetic field. And therefore, you can have electric field and magnetic field coexisting. And so we have electromagnetic field. Again, coming back to what a field is, a proper definition for a field, we say it's a spatial distribution of quantity. It's a spatial distribution of a quantity. And it may or may not be a function of time. If the field is static, it may not be a function of time. But if it's dynamic, it may be a function of time. And as we said before, a time-varying electric field is accompanied by a magnetic field and vice versa, which means that a time-varying magnetic field is also accompanied by an electric field. And you know that the electricity that is generated, let's say from the Akosomo Dam in Ghana here, comes about as a result of coils rotating within a magnetic field, or vice versa, or a magnetic field rotating around coils. So when the field is rotating, it is time changing. It will induce current in the coils. In this case, you have a magnetic field that has created what? Electricity. So a time varying magnetic field is then accompanied by an electric field. So whether we start with the electric field first or we start with the magnetic field, if it's time varying, we'll get the other. So that a time varying electric field is accompanied by a magnetic field. And a time varying magnetic field is also accompanied by electric field. In other words, the electric field and the magnetic field, they are coupled together. So we have what is called the electromagnetic field. As I said, the time varying electric and magnetic fields are coupled, resulting in an electromagnetic field. Now, a situation can be created where the time-dependent electromagnetic field can produce waves. The waves are those that propagate, and therefore radiate outwardly from the source and to provide connectivity, for example, in a cell phone network. So the field is created, and then it is changed into a wave because it is time moving or time varying, and it propagates in the form of a wave. If you have observed the phenomenon of dropping something in a river or in water, you see that it will create waves. Similarly, you have a time-dependent wave or time-varying field. It can propagate in the form of waves. And if it does that, it will radiate away from the source, and therefore it can carry message, or a message signal can be impressed on this wave to a distant destination. Because if you observe a wave on the sea that starts from a very far away, can propagate all the way to the seashore. Same way, the electric field and the magnetic field that are coupled together, they can propagate as a wave from the source to a distant location. And therefore, we can impress a message signal on this wave and allow the wave to carry it from one point to another. And this is the basis for wireless communication. So it is electromagnetic fields and waves that make wireless communication possible. In other words, this course is the basis for understanding wireless communication. But for you as electrical engineers, why is this course necessary? Because there are so many electromagnetic phenomena that you would have to deal with as electrical engineers, from actuators to even the generation of electricity itself, where electric field is coupled with a magnetic field, resulting in the production of electricity, to so many other applications. You require an understanding of electromagnetic field to be able to properly comprehend that. But dominantly, wireless communication is made possible through the understanding of electromagnetic fields theory. Again, another perspective to help you understand electromagnetic fields theory better is to look at circuit theory versus electromagnetic fields theory. You're familiar with circuit theory. Let me give you a little background about circuit theory. In circuit theory, we assume that the component within the circuit, let's say for simplicity, a resistor like this. This resistor has a dimension in terms of its length proportional to the wavelength of the current or voltage that passes through the resistor. What do I mean by that? If you have a sine wave that is like this, the full cycle is one wavelength. So let's say you're dealing with electricity, which is at a frequency of what? 50 hertz. At a frequency of 50 hertz, what is the wavelength? It will be 3 times 10 to the power 8 divided by what? 50. 50 hertz. So if you look at this one, the ratio is still very big. So that means that this wavelength is so huge that from the beginning point of this resistor to the ending point of the resistor will be a small fraction of this wavelength, lambda here. Let's say a resistor is 1 millimeter. If a resistor is 1 millimeter long, this ratio, this is 30 divided by 300 divided by 50 is what? 6. So this is 6 times 10 to the power what? 6, which is actually 600 what? or 6,000 kilometers. This is 6,000 kilometers. 6,000 kilometers, it means that for a signal which has a wavelength of a frequency of 50 hertz, the wavelength is 6,000 kilometers. Compare 6,000 kilometers to 1 millimeter. 1 millimeter is very insignificant. So if you're looking at this wave and you're saying that it changes, the amplitude changes as you go from one end to the other.
No, that's not the movie you're supposed to.
If you're looking at this wave and you're looking at the wavelength, which is 6,000 kilometers, you can see that 1 millimeter is nothing compared to 6,000 kilometers. So if we had to put the resistor along the path, along this wavelength, if you are starting from 0, 1 millimeter from 0 would actually keep you still around what? The same point. And therefore you can see that the amplitude is still what? The same. So in the case of circuit theory, the approximation that is made is that there is no variation in terms of the voltage and the current as you move from one point of the component to the other point, because it is very small compared to the distance of the wavelength. And because of that, voltages and current are what? Discrete. So you can talk about 5 volts. You can talk about 2 ampere. They have specific value because it's constant. But if you consider a very short wavelength, let's say this wavelength is 1 micrometer, for example, then you can see that along this resistor, which is 1 millimeter, the wave would have changed several times from one end to the other. So that the voltage here will be 0, but the voltage here is not 0. And therefore, in the situation where the wavelength is comparable to the dimension of the component, you cannot have a discrete value like 5 volt or 2 ampere. You have to talk about the voltage per unit length along the component. So the differences in frequency is the most significant difference between what? Circuit theory and electromagnetic field theory. In circuit theory, you're dealing with very low frequencies and therefore very large wavelength. But in electromagnetic field theory, you're dealing with what? Very high frequencies and therefore very short wavelength. And therefore the treatment is different. Another key example, if you look at this telephone, those of you who are old enough will be familiar with telephones like this during the launching of Mobitel, the first mobile communication company in Ghana. In circuit theory, this antenna here, which terminates at this point, will be considered as an open circuit. I hope you follow. Because in circuit theory, current will flow when there is what? A complete circuit or a closed circuit. But if you look at this antenna, you may be tempted to conclude that the tip of the antenna provides what? An open circuit, because if a current is flowing here, it will reach the tip of the antenna and there is no continuity for the currents at the tip of the antenna. And therefore, how is it possible for us to have wireless communication? Understanding that is explained by what? Electromagnetic field theory. Because you cannot use circuit theory to understand how one phone is connected to another phone through the antenna. Because as far as circuit theory is concerned, the two antennas, there is no connection between them, so there's open circuits and nothing can flow between them. But this can be explained properly by electromagnetic field theory. As I said, the time varying current, when it reaches a point of discontinuity here, it changes into a wave that propagates. And this wave will propagate, and the message that is coming from the phone is impressed on the wave, and therefore it can carry it to another antenna and induce the same message in that antenna at another distant location. So same principle is used for television reception, as well as Wi-Fi, Bluetooth, and all of these things. They all work on the principles of electromagnetic fields theory. Without electromagnetic fields theory, none of this will be possible. Television will not be possible. Phone will not be possible. Wireless communication, as in Wi-Fi and Bluetooth, will not be possible. Microwave heating will not be possible. All of these are made possible by the understanding that scientists had of electromagnetic fields theory. So the things that we look in this course are introductory concepts, which we are looking at currently. And then next we'll look at static electric fields, static magnetic fields, and we look at time varying fields. And that is where we'll end as far as your class is concerned. There are some textbooks that I recommend for those who are interested in getting extra materials, and they're here listed. You have them in the PPT already. Fundamentals of Engineering Electromagnetics by David K. Chen, Fields and Wave by the same author, and there's Microwave Engineering. The first chapter also gives an introduction of electromagnetic fields theory. So as usual, continuous assessment will be 30 and end of semester exams will be what, 70. And on this website, you can find all the course materials for this course. So basically, that is the introductory aspects of the course. And now we'll look at the first lecture of the course, where we'll try to understand what is called the electromagnetic model. To understand the electromagnetic model, let's look at circuit model. In circuit model, we have quantities such as voltage, current, resistance, inductance, and capacitance. These are all quantities. And the operations that are involved in circuit theory are usually algebra. When we do division, if you're finding current from voltage and resistance, or multiplication, if you're finding voltage from current and resistance, it's mostly algebra and some ordinary differential equations and some Laplace transforms. And I think in your circuit theory class, you may have used some ordinary differential equations, but maybe not Laplace transform. You may have used Laplace transform in, I think, well, in third year when you do classical control systems, you use Laplace transforms. Or in signals and systems, you use Laplace transform. So the rules of operation for circuit theory model is mostly algebra and ordinary differential equations. And the circuit theory has fundamental postulates. One such fundamental postulate is what? Kirchhoff's voltage and current laws. And you see that throughout your study of circuit theory, you apply this Kirchhoff voltage and current laws. So similarly, we have what we call the electromagnetic model. This electromagnetic model also has basic quantities. What are the basic quantities? The basic quantities can be divided into two categories. The two categories are source quantities and field quantities. So what are source quantities? The source quantities are the source of electromagnetic field. And these are either electric charges at rest or in motion. And I have repeated this several times that the source of the electromagnetic field is the electric charge. And therefore, the symbol of the charge is either Q or upper Q, like this. And the charge exists in integral multiples of the charge on an electron, which is minus E. So electron is 1.6 times 10 to the power minus 19 coulombs. So charge is measured in what? Coulombs. And a coulomb is a very large unit for electric charge because it takes 1 divided by the charge on an electron to get what? 1 coulomb, and which is about 6.25 million trillion electrons to make up 1 coulomb. And that is how much 1 coulomb is of electrons charge. And the fundamental postulate is a principle of conservation of electric charge, which means that the electric charge can neither be created nor destroyed. In the universe, there's a constant amount of charges. So when you create charges, or when you think that you are creating an electric charge, it is just merely separating existing charge from, say, their mother atoms. And then under certain conditions, they can recombine again and disappear. So charges can neither be created nor destroyed. Now, charges may exist in different forms. So you may have charges existing within a volume, and then it can be described by a volume charge density, which is the ratio of the charge to the volume in the limit as the volume approaches zero. So we are talking about a very small volume, and the charge within that volume constitutes a volume charge, and therefore it can be described by a volume charge density. And as you can expect, the charge is measured in coulombs, the volume is measured in what? Meter cube. So we have coulomb per meter cube. And then we can also talk about surface charge density. So on a surface, you can have a certain amount of charge within a very small surface area. And that's the ratio of that will give us the surface charge density, also measured in coulombs per meter squared. And you can also have a line charge density, which is the ratio of the charge to the line on which the charge exists. And that is measured in coulombs per meter. And charge densities could vary from point to point. And therefore, rho v, which is volume charge density, surface charge density, and line charge density are point function of space coordinate. It means that at different space, the value of the densities may be different. And as we have seen, the current is the rate of change of a charge, which is I is the Q by the T. So the ratio of the charge to time, the rate of change of charge within time. So as the charges are changing or moving, then they create what? Current. And therefore, the definition of the current is the rate of change of charge with time. And usually current is measured in ampere. So just as we have charge densities, we can also have what? Current densities. And when a current flows through a finite area, we have a current density. And the current density, usually denoted as J, is a measure of the amount of current flowing through a unit area normal to the direction of flow. So if you can imagine a wire, and then you cut a cross-sectional area of the wire, you're looking at the cross-section of the area, the amount of current flowing through that cross-section is what gives you the current density. So the magnitude of the current density is in current per unit area or ampere per meter squared. That's how it is measured. So these are the source quantities. The source quantities are what? Charges. And when they move or when they vary with time, they constitute current. It may be a current density or just simply a current. And these are the source quantities. We also have the field quantities, and there are four. And throughout the study of electromagnetic fields, you would have to deal with these four quantities. The four quantities are also vector field quantities. It means they have magnitude and direction. So we have the first one is electric field intensity, which describes the strength of the electric field at any point in space. How intense the field is at a point in space. If you look at this in terms of the cell phone, the cell site of a cell network, at the base of the tower, the signal may be strongest. As you're moving away, the intensity of the field will keep reducing until you get to the edge of the cell site where the field will be the weakest. So the measure of the strength of the field is called electric field intensity. And that is denoted by E, and it's measured in volts per meter. Electric field intensity is measured in volts per meter. The second one is the electric flux density, or electric displacement D. And now I'll talk about electric displacement in the last chapter because it's a very important quantity. But for now, the electric flux density is useful in the study of what? Electric field in material medium. Because when you have a material that is placed in electric field, the field modifies the charge distribution within the material, and it creates another quantity we call the density of the flux within the material, which is called electric flux density. And similarly, we have magnetic flux density, which you learned in applied electricity, and magnetic field intensity, which you also learned in applied electricity. If I may refresh your mind, in applied electricity, you learned about what? The BH curve. the BH curve, which relates the magnetic flux density to the magnetic field intensity. And the relationship between the magnetic flux density and the electric field intensity was what? B equals mu H. Similarly, there's a relationship between the electric flux density and the electric field intensity. Actually, D, which is the flux density, is given by epsilon times E, which is the electric field intensity. But we'll study this a bit later on in greater detail. So as I said earlier, the electromagnetic model has quantities, also rules of operation, as we saw with the circuit theory model. In the circuit theory model, we have quantities, voltages, current, resistance, inductance, and capacitance. Rules of operation, algebra, ordinary differential equations, fundamental postulates, Kirchhoff's voltage law. In the electromagnetic model, we have quantities. We can divide those quantities into two. We have source quantities, and these source quantities are what? Charges or current. So charges and current, if the charges are moving. And the field quantities are four, and they are electric field intensity E, electric flux density D, magnetic field flux density B, and magnetic field intensity H. These are the field quantities. So in summary, the fundamental electromagnetic field quantities are, for the electric field, we have the electric field intensity E, measured in volts per meter, electric flux density D, measured in coulombs per meter square. Then for the magnetic field, we have the magnetic flux density B, measured in Tesla, and the magnetic field intensity H, measured in amperes per meter. And so there are also some universal constants. I use one without making reference to it. The first universal constant we're looking at is C, which is the speed of an electromagnetic wave. You are familiar with the speed of light, 3 times 10 to the power 8, is the same quantity here we are referring to C. Because light is actually a portion of the electromagnetic spectrum, electromagnetic wave spectrum. The light is actually a portion of this spectrum, as we shall see a bit later. And so the speed of all electromagnetic waves is what? C, 3 times 10 to the power 8. And then permittivity of free space is another universal quantity, epsilon naught. And the permeability of free space, mu naught. Epsilon naught relates the electric flux density to the electric field intensity. Mu naught relates the magnetic flux density to the magnetic field intensity. And these are their values. The velocity of light in free space, or the velocity of electromagnetic wave in free space, is 3 times 10 to the power 8 in meters per second. And the permeability of free space is 4 times 10 to the power minus 7 in henries per meter. Permittivity of free space is 1/36 pi times 10 to the power minus 7, and this is farad. Sorry, this is farad per meter. This is farad, not henries per meter. So they are called the universal constants. And as I mentioned before, this is the relationship between electric flux density and electric field intensity. It's called the constitutive relations. D equals epsilon naught E in free space, and B is mu naught H in free space. And C is given by 1/square root of mu naught times epsilon naught. If you compute this from the values that we showed here, this is mu naught and this is epsilon naught. If you use that here, you get 3 times 10 to the power 8 meters per second. So this is the initial introduction that we have of the course. When we start the first or the next topic, which is a static electric field, then we will discuss the rules of operation in that field as well as the fundamental postulates. But for now, we know that in the electromagnetic model, we have two quantities, source quantities, which is electric charge, the electric charge, or the charge density or current density. And then we also have the flux density, electric field intensity, magnetic flux density, and magnetic field intensity. So next, we'll talk about the various, if you want, fundamental postulates. We said in relation to circuit theory that the fundamental postulate is what? Kirchhoff's voltage and current law. In the electromagnetic field or the electromagnetic model, we will also come to see what are the fundamental postulates in our next class. At this point, if you have questions, you can